It's a pleasure to welcome Ping Chang to talk to us. So Ping is a longtime friend of the project and has an amazing database, which I guess he's just about to tell you about on the EERIE simulations. And we were just planning some collaboration just then. So and there's more that we're planning to do with him. So Ping, take it away, please.
Well, thank you, Malcolm, and thank you for inviting me to share some our results with your group. And as Malcolm said, we're looking forward for potential collaborations with your project team. And as some of you may already know, so we've been doing this high-resolution CESM simulations for quite some time now. So the project started initially as a collaboration with Chinese colleagues, and but of course, because of the national security reasons, the project was terminated, and now the project is entirely supported by the U.S. Funding agencies, and particularly the NSF. So the project has a new name. It's called MESACLIP. It's purely an NSF-funded project at this point. So there's a long list of the people participated in this project. Because of the time constraint, I'm not going to tell you all the names here. You can read the list here. So just give you a quick tutorial about the model we're using for this project. So the model we're using is CESM version 1.3, and the atmospheric resolution is 1/4 degree. And the ocean resolution is 1/10 degree. And so we're not using the latest version of CESM-2, and primarily for two reasons. One is the CESM-2 does not have a high-resolution configuration. NCAR and the CESM community never decided not to put forward a high-resolution version. And the second reason is that the CESM-2 are substantially more expensive computationally. So we actually want to keep things computationally light, and so that we can make ensemble runs. So I'm just going to give you an update, the runs we have done so far. And so this is the first set we did, which is a contribution to the high resolution MIP phase 1 project. So this is the first set of the experiment. We call it a high resolution MIP set. And then this is the big set. The second set is the CMIP style DAC set. It consists of several simulations. The first is a pre-industrial control simulation at the 1850, and we run the model for 650 years. And then we branch out from these runs. We did an ensemble of 10 1920 to 2004 historical climate simulations. And then after that, we did a future projections. So we completed ensemble of 10 2005 to 2100 climate projection under RCP 8.5. And we also completed another projection under also ensemble 10 under RCP 6.0. And then we did 2 single simulations under RCP 4.5 and 2.6. And we also did a 1% CO2 simulations and quadruple CO2 simulations for the climate sensitivity studies. And in addition, we made our ensemble of 3 AMIP simulations from 1950 to 2014. So that's the set that's been completed already, and we're currently expanding the AMIP ensemble size. We also want to make the AMIP to 10 member, so that we have a more complete simulation. So in addition, we also did a decadal prediction ensemble, and so that has 2 components. One is we initialized a couple of models using the forced ocean sea ice 4C simulation to run the high resolution ocean component of the model from 1958 to 2018, 5 cycles. And we used the last cycle to initialize our decadal prediction. So the prediction contains two initialized dates, and one is November 1st, and the other one is May 1st. So we have a November ensemble, then the May ensemble. So each ensemble contains 5 years and 10-member decadal prediction. And so we in the process of completing all the ensemble predictions initialized for each year. And so the November set is almost done. A few more prediction needs to be done. And we just started with the May initialized so far. So that's a big, very expensive simulation set. So far, if you counted all the simulations, we completed more than 6,000 years high resolution simulations. And we generated about 7 petabytes of data sets, which is a big problem for us. And because we got a lot of requests when people want to use these data sets, and sharing data is a big challenge for us. So for today's talk, I'm going to be trying to focus on one of the current research we're doing, which is on the extreme precipitation. So we did quite a bit of analysis trying to understand the difference between the extreme precipitation in the high resolution model and the low resolution model. So I hope some of the analysis where I'm showing you today can be also applied to your simulation. So first, just let me show you a comparison between the observed and the simulated extreme precipitation. And we're just using this the annual maximum daily precipitation as a metric for the comparison. So the panel on the left is showing the observed HUD-X3 RX1 day extreme precipitation distribution over the globe, and all the way from 1920 to 2018. And then the picture in the middle is showing the high resolution CESM simulation for the same period. And then the picture on the right is the simulation results for the low resolution model. So you can see that the high resolution model is doing much better in terms of capturing the amplitude and the intensity of the extreme precipitation. And if you take the global mean value, which is you can see the number below each figure, you can see the high resolution model actually gets a lot closer to the low resolution model. Of course, we want to understand why is the high resolution model is doing such a better job, given that the atmospheric resolution, we're not resolving convection. We're still running the atmosphere at a quarter degree with the same convection scheme using the low resolution model. So that's one of the things we're trying to understand. So the first thing we did is that if you look the component of the precipitation, right? So in the model, there's a resolved precipitation component, and then there's a parameterized component. So first, if you take the difference between the high res and the low res, in other words, if you take the picture in the middle and minus the picture to the right, you get this bottom picture here, bottom left picture. So that's the changes of the extreme precipitation after we increase the after we increase the model resolution, right? So if you look the contribution, this difference, which component of the precipitation contributing to this difference, and what we found is that most of the contribution is actually coming from the resolved component. So it is even if we only increase the atmosphere model 4 times, and the model is actually resolving the extreme precipitation much better, and so we get a significant increase of the extreme precipitation from the resolved component. So if you look to parameterize the component, in fact, you actually see the opposite. In fact, the high resolution model is actually getting less extreme precipitation from the parameterized precipitation. So that's kind of interesting. So that motivated us to look into further to understand exactly what physical process causes this resolve the between precipitation increase in a high resolution model. So what we did then is actually did a extreme precipitation moisture budget analysis. And so there's a couple of nice paper written by the UCLA group and published in 2019, and basically lay out a procedure to do the extreme precipitation moist budget analysis. So basically, the equation is written here. I hope you don't mind. I show a few equations here. So the you can write the extreme precipitation is equal to the evaporation, and then the moist flux convergence, which is these two terms here, right? We split that into a components driven by the flow convergence, and another is the moisture advection, and this is the tendency term. And the curly brackets represents the vertical integrated all the way from the surface to the top of the atmosphere, right? So if you read this two papers, it turns out that for the extreme precipitation, there's a very substantial cancellation between the moisture advection and the tendency term. And evaporation turns out to be a very small contribution. So therefore, the extreme precipitation is approximately given by this flow convergence driven moisture convergence, right? So now what we can do, we have this approximation. Now what we can do is that we can take the difference of the extreme precipitation between the high resolution model and the low resolution, which is this equation, right? So the difference of the extreme precipitation delta T E superscript E, which is the extreme precipitation difference in the high resolution minus the low resolution. That is approximately given by this term here, the flow convergence driven moisture flux convergence. And you can split this term into three terms. One is due to the moisture difference between the high resolution model and the low resolution model. And the other term is due to the convergence, local convergence difference between the high resolution model and the low resolution model. And then the last term is the nonlinear term, right? So the first term, due to the moisture difference, is what is called the thermodynamical tendency. And the second term is called the dynamical tendency. So what we want to do is to see which of this term is actually causing the model. Is it really the moisture difference between the high resolution model and the low resolution model, or it's really the local flow convergence, which is given the extreme precipitation difference. So this is the results we find. So if you compute each of this term, right? So this is the extreme precipitation difference between the high res and the low res. And this is the approximate term. This is the difference of the moisture flux convergence driven by the flow convergence, right? The ones I just showed you from the equation. And you can see, indeed, this term gives us a pretty good approximation to the total precipitation difference between the two models. So now if you look the contribution from the dynamical tendency, thermodynamical tendency, and what you can see is that most of the difference is actually coming from the dynamical tendency. In other words, the biggest difference between the high resolution model and low resolution extreme precipitation difference is actually driven by the local circulation, which drives the flow convergence difference. So that's one of the interesting results we find. So after we did this, then of course we want to know what physical phenomenon really governs this circulation difference between the high resolution and low resolution. So we did another analysis, and there's a really nice paper published last year by Andreas Prey and his colleague. And basically what they did is that they actually derived a multi-object analysis of atmospheric phenomena called a MOAB package. And this package allows you to track 15 different atmospheric phenomena, which can potentially give rise to extreme precipitation. So all the phenomena are listed over this table: surface cyclone, mid-level cyclone, cutoff lows, tropical cyclone, anticyclone, jets, ARs, and mesoscale convective systems, and then all the fronts and all the equatorial waves. And so those are the potential phenomena can give you the extreme precipitation. So, and what Andrea did is that he applied this this analysis package to the EERIE 5, the data, and combined with the GPM iMerge precipitation data, and also the merged infrared data. So then that allows him to track all the phenomena which relates to the potentially can cause extreme precipitation. So what we decided to do is to do the same analysis using our model runs. The only problem is that in order to run this package, we have to have the hourly output of data. And we didn't save the hourly output. Initially, we only saved most of the runs. We saved 6 hourly output. So what we decided to do is to rerun one of the ensemble member from the same period, 2001 and 2020, and save the hourly data from both the high resolution runs and the low resolution runs. And then we did the tracking, and then we can compare our model simulation and to the reanalysis, and to see to what extent the changing model resolution can better capturing this kind of atmospheric phenomenon. So I'm just going to walk you through some of the results. Some of the results was quite surprising. So this is basically a two-dimensional PDF distribution. Indicates the typical length scale and the temporal scale of different phenomena. So each of this color represents the different atmospheric phenomena. The black represents all the cyclones, orange, the anticyclone, the green showing the MCS, and the red is ARs and so on. So the left is, this is basically from Andrea's paper. And so the vertical axis here is time, and the horizontal axis represents the spatial scale. So this gives you a kind of a depiction of the characteristic scales, temporal scales, and the spatial scales of different atmospheric phenomena. So the middle panel here is showing the high resolution model simulation, and the right panel here is showing the low resolution model. So you already see that there's actually a quite significant difference between the high resolution model and the low resolution model, right, from this distribution map. And the high resolution model is surprisingly close to the observation, which was very surprising to us. And even the MCSs, right, so which is the green curve here, the green contour here, seem to match with the observation quite nicely, which is really surprising to us. So the bottom picture here is basically showing a one-dimensional picture of the upper. You project that into the one-dimensional. So in the left panel is showing the spatial scale, and the horizontal showing the different atmospheric phenomena, and the black is showing the observation. The red is the high res, and the blue is showing the low res, and the right panel showing the temporal scale. So one particular thing I like you to pay attention to is these MCSs, and you can see the model is actually capturing the spatial scale of the observed MCSs quite well. It's about 300 to 400 kilometers, and the high resolution is reproducing that nicely. But the low resolution model producing a much larger scale. We're looking at the MCS is close to about 1,000 kilometers, right? So what this thing can have an impact on the extreme precipitation. So here is another way of looking at the difference of the MCSs. in the model, in the high resolution model and low resolution model, and compare it to the observation. Again, the left is showing observation, the middle panel is showing the high resolution CESM simulation, and the right panel is showing the low resolution. Notice that the vertical scale has changed. So the color bar represents the this occurrence frequency. So how many days MCSs occurs in a year on average, right? So notice the low resolution essentially have no MCSs, right? So the vertical scale is very different. It's much smaller color bar here. The high resolution model, on the other hand, even though it's not perfect, but it actually reproduce the general characteristics of the MCSs quite nicely, which is quite surprising to us. So now, how does this MCSs has to do with extreme precipitation? So this bottom map is showing the most frequently occurring phenomenon during the extreme precipitation day. So at each grid point, we identify the dates that extreme precipitation occurs. And then we're looking for the physical phenomenon occurs during this time period, right? So then you can map this out globally. And so again, the left panel is showing the observation, the middle is showing the high resolution model, and the right is showing the low resolution model. And the red color here is MCS. Sorry, we changed the color. So the red is the MCSs. So you can see in many areas in the tropics and the subtropics, even the mid latitudes, lots of the extreme precipitation are associated with MCSs. And the high resolution model, again, it's not perfect, but it starts to representing this MCSs produce extreme precipitation quite well. And the low resolution model, on the other hand, is showing completely wrong picture, basically saying all the extreme precipitation in the low resolution model are associated with either jets or fronts. There's actually absolutely no indication of the extreme MCSs. So if you look the recurrence frequency of the fronts and the jets in the observations and in the high resolution model and the low resolution model, you can see consistent with the analysis I showed you earlier, the low resolution model basically have way too many fronts and the jets. And so that's there's some really fundamental difference between the high resolution model and the low resolution model simulation results. So
about 3 minutes, Ping. Okay.
Okay, so I'm almost done. So this is the last picture I want to show you. So with these improvements, now we can look the projection into the future. So this is the projected extreme precipitation changes. The top panel is showing the high resolution model. The bottom panel is showing the low resolution model. So the left panel is showing the total projected extreme precipitation increase or change in the high resolution model and the low resolution model. And you can see the high resolution project almost twice as the increased rate of the extreme precipitation compared to the low resolution model. And what is interesting is that there's a fundamental difference of the driver of the extreme precipitation increase. In a high resolution model, the dynamical contribution, the dynamical tendency is a major contribution for driving the future extreme precipitation change. In a low resolution model, it's the thermodynamics which driving the extreme precipitation change. So there's fundamentally a difference in terms of the physics of the dynamics in driving the future extreme precipitation changes when you increase model resolution. So that's basically the results I want to share with you. I hope we can do a similar analysis with the simulation data sets you guys have. I think that'd be really wonderful. So here's a summary. What we have found so far, and I think Malcolm just asked me to mention a few ongoing projects. And so in addition to the extreme precipitation dynamics analysis I just showed you, the other project we've been working on is the pooling trends in the Southern Ocean and in the Southeast, the tropical Pacific. And we we have some ideas. We're still working on that. We're doing more process-oriented experiments, and I'll be very happy to talk to you more about this. And the other focus area we're working on right now is the coastal sea level rise. And we actually found a lot of difference between the high resolution model and the low resolution model in terms of simulating the future sea ice, the local coastal sea level rise. So finally, I just want to mention, the data release plan. And so we're currently trying to finish up a paper. Basically, we're writing up these results for the extreme precipitation analysis. We're trying to get this thing submitted. So as soon as this paper is submitted, we're going to release the data to the community. So our target is the end of this month. And we're trying to release all the ensemble simulations to the community. So I'll end here. Thank you very much.
Thank you very much. That was fantastically interesting. Thank you. Yeah, that was great. Questions? Let me try and spot any questions. Maybe I can ask. So I'm also amazed that the model can do such a good job of, I guess, the precipitation associated with MCSs, and it doesn't. So you kind of, I mean, I guess this is daily extremes rather than hourly, but you kind of get the impression from kilometer scale modelers that you have to go to kilometer scale to get the extremes, right?
Yes.
But from your results, there's not much room left, right? On the daily, you would struggle to do better than your simulations suggest.
But that's why we're so surprised. Initially, we didn't expect
Yeah.
it, right? And but then, if you look to track the results, the typical spatial scale of the MCS is about 300 to 400 kilometers. So if you have a 25-kilometer model, you stop, yeah, right? But if you have a 100, if you have a 100-kilometer model, you're not going to be able to resolve something to 300 to 400 kilometers. So, so I guess there makes some sense. Even we don't go all the way to the resolving, we start getting something correctly. So, but that's not to say that we don't need to increase the model resolution further. I believe that if you go further to the cloud resolving scale, the results may be even better. We can even look at the hourly extremes or even daily extremes, right? So but then to quarter degree or so, we already see some major improvements, which is quite surprising.
Yeah. Jinsong?
Yes, thanks for the very interesting talk. I just wondering, you said that the flow convergence is important to producing your extreme precipitation. And is that related to vertical velocity?
Yes, absolutely.
Yeah, so that's also, okay, that's also what we see if we increase the resolution, what you see as the first is the vertical velocity.
Absolutely, yes, the flow convergence.
And one more very quick question, is that hydrostatic or model?
This is hydrostatic model.
Okay.
This is not non-hydrostatic because we're not at the cloud resolving yet. We're running at a quarter degree. So we use the same convective parameterization as the 1 degree model.
Thanks.
Okay. Anne-Marie?
Yes, well, thank you for this very interesting talk. I am an oceanographer, so I'm going to ask a very basic question. I hear, like everybody, that when we move to a warmer climate, there is more humidity in the air, and this is going to do more precipitation. And then you say in the model, the main driver is not the amount of moisture in the future, but the change in the convergence. So could you elaborate a little bit more? Why in the future would this change in convergence, or like Jin-Song said, the change in vertical velocity, why would that happen in the future climate?
Yeah, and so there's a lot of recent studies on this, to what extent the moisture change is driving the future extreme precipitation change, or whether the circulation change is important. So if you look at a regional scale, there's a study, for example, I think at by UK group, looking at the future change of the extreme precipitation. What they find was that as the temperature warmer above certain thresholds, what they find is that the precipitation actually stop increasing. In fact, if you look at the data, right, there's a lot that's called a hook phenomenon. So when the temperature is below a certain threshold, you actually see the precipitation increase as temperature increases. But when you get to a certain temperature threshold, then you actually don't see the precipitation increase anymore. So one of the reasons for this potentially could be due to the circulation regime shift. For example, if the temperature gets too high, then the local weather pattern is dominated by the anticyclonic circulation, right? So you don't get this the uplifting of the moist air anymore. So you basically get the heat waves that dominated climate. So that can actually change the precipitation increase. So there's a lot of recent studies basically pointing out the importance of the dynamical circulation change in driving the extreme precipitation. So the early study, there were lots of emphasis on the thermodynamics and people using Clausius-Kaplan relationship, saying that 1 degree increase translate to about 7% precipitation increase. But that is true as you see that in the low resolution model, right? The thermodynamics is basically dominating. The moisture change is the important factor. But when you go to regional scale, when you go to higher resolution, then you start to see the circulation change also plays an important role.
So I've got 3 more questions that I can see. If people want to take their break, then please do to start again at in a few minutes' time. But we'll keep going through the questions. Christian?
Yeah, thanks. Really interesting. There can be a lot of uncertainty in observational estimates of extremes in particular. I wonder if have you compared to using, say, rain gauges over particular locations? I mean, if you compared the high-res model to rain gauge estimates, would it still look as good?
Yeah, we didn't do the rain gauge, but we actually looked at the satellite data. I have a picture just to show you so this is using the GPM iMerge data sets. And so in the bottom, and we're using a different metric for the extreme, but this time we're using the 99 percentile as a measure of it. The basic results is very similar. It holds up. So the top panel here showing the RX1 day, the station-based data, but the bottom is showing the satellite data. So again, the high resolution model is doing much better than the low resolution model. But we have not done, at a single station, we did not look at a particular station data and look at the model yet.
Yeah. Okay. Thanks.
Nikki?
Well, thanks a lot. Anne-Marie actually asked my first question, which is about the thermodynamics and the role of that for driving the future changes in extreme precipitation. So the first question is a bit sort of provocative. Well, I mean, if you go to finer and finer resolution, I mean, the convergence has to become more important than thermodynamics because, I mean, let's say at a global scale, it's all thermodynamics. And if you chunk it up to smaller and smaller scales, I mean, it's natural for the advection and the convergence or divergence elements to become more important relative to the thermodynamics. So if you go to high resolution, part of that could just simply be because you're finally resolving the motions rather than having the thermodynamics kind of taking over part of the advective components. Is that a correct view? And the second question, let me ask it maybe more simple, is what is the role of increased topography when you go to higher resolution in driving extreme precipitation?
Yep. So let me ask you a second question because it's easier to answer. The topography definitely plays a very important role. In fact, if you look at the high terrain region, there's obvious improvements of the simulation when you increase the resolution of the model, because we're actually resolving the steep topography much better So topographic lifting, process is actually better represented in this. So there's definitely impact on that. So for your first question, I think that's right, but I think, one of the things I learned from Andreas' analysis, and one of the argument he put together for this extreme precipitation, he argues that to really understand the extreme precipitation, we have to understand the multi-scale interaction of different atmospheric phenomena. So for example, those MCSs, the MCSs are typically generated because multi-scale interaction of different atmospheric phenomena. For example, you have a cold front, right, coming from the north, and then you have a warm, moist air, let's say the Amazon River transporting moist air northward. Then when these two phenomena collide to each other, right, you're getting a frontal system, and that's a initiation of the MCSs. That's where the large-scale convective system got developed and got a lot of the extreme rainfall. So if you cannot represent this kind of multi-scale interaction correctly, then you fundamentally are not capturing this physical process driving the extreme precipitation. So I think what we're more interested in, what we think is that the high resolution model is doing better because it represents, it's capable of capturing this multi-scale interaction process in atmosphere.
Yeah. Well, I totally believe you.
Oh.
By the way, I have the chance now to talk about Andreas because he just joined our faculty a couple of weeks ago. But
Yes.
Thank you.
Yes, I think that's, we've been discussing with him, and it's really, he has a lot of good ideas.
Yeah, we should do that analysis. Pierluigi?
Well, just a couple of comments. So, I mean, all of these ideas about the role of convergence as we increase the resolution were the topic of a paper by Marie-Estelle de Marie many, many years ago before we did Primavera. And it was then picked up by Benoit Vanier later on in Primavera. And so these are sort of the foundations. But then, as you were saying, so and orography definitely is a part of that. And Benoit Vanier did some sensitivity studies in which he looked at how much of this is then enhanced by orography. But just to go back to what you were saying and getting to my point, which is about MCSs. So when I was doing my master's in the US, I was studying this diurnal convergence at the center of the US, and the fact that you have the Rockies and Appalachians, and you have this diurnal cycle of convergence, and this is the big avenue for MCSs. You need to have this moist flow coming from the Gulf.
Exactly.
So you need to have all these ingredients, and the models at this scale start to do all that.
Right.
And so in certain places of the world, it is, and the Sahel is another one, it is expected that all of these ingredients then form things like MCSs. Now, to get to Malcolm's point, I have a question. So we also at 10 kilometers see an astonishingly good comparison between the MCS precipitation and the observations. However, when we look in detail and we look at the intensity, frequency, and size, we see that we come to the right precipitation for the wrong reasons. So the MCSs are way too big, there are way too many, and each one of them rains too little. So have you looked at this?
No, I mean, that's the plan. We're actually going to try to work with Andreas and look at the things at a much more detail, and we're trying to break down into different seasons, as you said. There's a lot already indication that the model has problem, for example, in the Great Plain area of the US, that does not penetrating deep enough into the Great Plain area. So I'm sure there's still lots of problems with the model at this resolution.
Yeah.
But I think the point we're trying to make is that even at this resolution, we start getting something look more realistic, more similar to the observation. And so the point we're trying to make is that perhaps this kind of resolution model can increase the confidence for us to project into the future how the extreme precipitation can change. Yes,
but I like your result about the jets. So I loved all your presentation, but the fact that we end up with basically fronts and jets doing most of the precipitation at the low resolution, that is beautiful.
Yeah.
There are lots of things I want to say. We can talk later.
Yes,
about,
I mean, I'm very happy to discuss with him. Yeah.
Lots of times the regional models say, oh, I can just downscale and do the same. Well, if you don't have the right circulation, certain things you can downscale, certain things you cannot.
Exactly.
Thank you very much.
So yeah, with apologies to Matthias, maybe you can post your question in the chat. We should move on because I know it's getting late, particularly in Europe. So thank you again, Ping. That was inspiring, I think. Kind of shows some of the things that we might be able to do with our simulations. So thank you very, very much.
Thank you so much.